Okay, so I'm going to talk about Riemann-Roch theorem today. And this is a theorem that has a lot of different versions and generalizations. And one of the goals of our seminar is to understand Grothendieck Riemann-Roch. But today I'm going to talk only about the classical version of this theorem as it was covered by Riemann and Roch. So the classical Riemann-Roch concerns the dimension as no. چی شد؟ The dimension of a certain مهدی من فکر کنم باید عوض کنم. صبر کن دوباره برمیگردم. برای شما هم قطع میشه دیگه این نه؟ Okay, so today I'm talking about Riemann-Roch theorem and the classical version of this theorem, which concerns the dimension of certain space of meromorphic functions on a Riemann surface. This theorem was discovered by Riemann in 1857 as an inequality and was extended by Roch in 1865 as an equality. So I'm going to tell you what this theorem is, the statement of the theorem, and I'll also try to prove at least one version of this theorem using analysis today. But I would like to give you different versions of this proof because as the Riemann surface viewed from many different points of views, a Riemann surface for Riemann was a finite branched cover of sphere. So any Riemann surface for Riemann came equipped with a function, which is a meromorphic function x to CP1, the Riemann sphere. But today we define Riemann surface differently. We say a Riemann surface, so modern definition, a Riemann surface is a complex one-dimensional manifold. So what it means is that you have a topological space and each point on this topological space has a chart. So you have an open neighborhood around that point, coordinate function phi from this chart to an open subset inside C. And these charts need to be compatible in the following fashion. If you have two such open charts and they intersect in a place like this one, you have two different ways of giving coordinates to these charts, phi and psi. And then you have a change of coordinates. So you have a map from here to here by phi inverse composed with psi. And we require this map to be holomorphic. If this condition satisfies, we say we have a one-dimensional complex manifold. And generalizing it to higher dimensions is very easy. All you need to do is taking open subsets in C, you take open subsets inside some power of C, C to the power n. And this way you can define n-dimensional complex manifolds. In fact, Riemann-Roch theorem has extensions to higher things as well. But today I'm going only to talk about the Riemann-Roch theorem as Riemann and Roch discovered it, so only for one-dimensional complex manifolds. Now, if you define a Riemann surface this way, a very non-theorem is that there exists a meromorphic function on this surface that is non-constant. So the existence of non-constant and meromorphic functions on X is non-trivial. And once you prove this, once you prove that there exists such a non-constant meromorphic function, let's call it Z, then the space of all meromorphic functions, K, is going to be a finite extension of C of Z. And this is another approach to define a Riemann surface. You can define a Riemann surface just by its field of rational meromorphic functions. So the second definition, definition 2, we can say a function field over a field K is a finitely generated field extension K of transcendence degree equals 1. What this means is that you find an element in capital K, let's say Z, such that K is a finite extension of K of Z. And this definition has the advantage of working over other fields, not just complex numbers. We can define this way something like a Riemann surface, but this is now an algebraic curve over field. And the field K doesn't need to be even algebraically closed. And there are versions of Riemann-Roch that work for non-algebraically closed fields. So that's the second definition. And the third definition of algebraic Riemann surfaces is this. An algebraic curve that's smooth and projected. Definition 2 and 3 are equivalent to each other. Definition 1 only works when K is C. So all these three definitions become equivalent once you work over complex numbers. And this is amazing because, as you can see, these definitions actually in different disciplines of mathematics. The first one lives in analysis. The second definition lives in algebra. And the third definition lives in geometry, in the realm of geometry. And there are other approaches to Riemann surfaces beyond these.
Can I ask
question?
Yes.
Yeah.
In the second definition, what is the Riemann surface then? It's the function field. It's called the Riemann surface.
Right. So you might ask what points, right? So what is the space and points? And the answer, the short answer to this question is that discrete valuations considered to be points on this Riemann surface. So the thing that I would mention without proof is that if you have two smooth projective algebraic curves over K, whose function fields are isomorphic, then they are isomorphic algebraic curves. And if you give me any function field, there is a unique up to isomorphism algebraic curve whose function field is given by that field. These are non-trivial theorems, but there are standard text that contains their proofs. For example, section 7 of Hartshorne in chapter 1 gives a proof of this fact. And the interpretation of a Riemann surface by field of rational functions actually is something that was discovered by Kingdom Weber in 1886 when they wrote a very famous book, which is translated into English, called, I think, function fields in single, function fields over complex numbers in single variable, something like that. I have that book actually. It's actually if you're interested in the history of mathematics and especially history of algebraic geometry, that book is a must read. It's very, very beautiful. Okay. Now, let me give you a few examples of Riemann. So the easiest, we only work with compact Riemann surfaces because if the Riemann surface is non-compact, then it might not be algebraic. So for example, if you have a Riemann surface with infinite number of poles, then it will not be algebraic. But if once you work with compact Riemann surfaces, then all of them are algebraic. So the simple one perhaps is the sphere, CP1, which we call it a Riemann surface of genus 0. The second example is a torus, which can be realized as C divided by a lattice. And this is a Riemann surface of genus. And if you want to a torus in an algebraic way via an equation, you probably have heard of the word elliptic curves, which are given by cubic equations, things like these. This is the equation of the elliptic curve in the affine coordinate system. If you want to make it projective, then you have to homogenize this and write as y squared z equals x cubed plus xz squared plus bz cubed. In order for this to be non-singular, to be smooth, you need to assume that 4a cubed plus 27b squared is 0. Non-zero. This way has the advantage of working over other fields. If you think of a Riemann surface of genus 1 as being C divided by a lattice, you can't really talk about field of definition. But if you write it as an equation, then it's easy to see what the field of definition is. I mean, if A and B are rational numbers, for instance, we say that the elliptic curve is defined over rational, defined over some quadratic field, for example, when you have an elliptic curve over that field. So this way you can work over any field. And you can actually define many Riemann surfaces as equations like these. You have like a homogeneous equation, a polynomial degree d, for instance. And you look at the zeros of this polynomial, and you think of these zeros as a subset of E2. Because it's homogeneous, then if x, y, and z are solutions, then lambda x, lambda y, and lambda z are solutions as well. And therefore, you can think of the solutions inside the projective plane, complex projective plane. And this is to be an equation of projective and smooth surface. Once you know that there's no point where all these partial derivatives vanish. If this, you might call it gradient of p, is non-zero on x, then this curve is going to be smooth and you have surface. Of course, it's not true that any Riemann is given like this by a single equation in CP2, but any Riemann surface is given by a family of equations inside some projective plane, projective space. It might be dimension more than 2. I'm not sure what is the smallest dimension that all Riemann surfaces are defined, but I believe that CP3 is enough. Any Riemann surface can be embedded in CP3. Okay. If you want to work in an analytic for Riemann surfaces of higher genus, something similar to the quotient of C by a lattice, you can do this, but you have to work with upper half plane. And this is a complex domain where PSL2R acts on it via Mobius transformations. So A, B, C, D acting on Z is AZ plus B by CZ plus D. And therefore, if you take, instead of a lattice inside C, a discrete subgroup gamma inside PSL2R, then you can do the similar construction as above and take H divided gamma. And this way you construct almost any Riemann surface of genus one. So another point of view that one can study Riemann surface is by hyperbolic geometry, because the upper half plane is where hyperbolic metric lives. And then the techniques from hyperbolic geometry comes into play. And in fact, the field of Riemann surfaces is so vast that it's fair to say that Amir Jafari spent all of her mathematics life just trying to understand what Riemann surfaces are. Oh.
Is this called the uniformization theorem? That every Riemann surface of genus bigger than one is a quotient of a.
Yes. So the uniformization theorem tells you the universal cover of Riemann surfaces, and they're either C or a sphere, CP1, or upper half plane, one of these three. And C appears for genus one case. The sphere appears only for the sphere, and the other Riemann surfaces have upper half plane as their universal cover. Yeah. Okay, so I want to tell you a little bit about the space of a meromorphic function on the Riemann surface. This is a field. It's also a vector space over C, and it's an infinite dimensional vector space. We want to work with certain finite dimensional subspaces and talk about their dimensions. That's the gist of Riemann-Roch here. So I have to define for you these finite dimensional subspaces. To do that, first I need to talk a little bit about order function at the point. So let me make a quick review. So suppose you have a Riemann surface X, and you have a meromorphic function, which is non-zero on this Riemann surface. Now, for any point P on X, you can define the order of F at P, which is the order of vanishing or pole of F at P. This order counted as a positive integer when the function f vanishes on P, and as a negative integer if the function f has a pole at P. And the way you calculate this order is very simple. You find a local coordinate at P, such that z of P is 0, and then you write f as some power of z times some unit. A unit function that is not 0 or infinity at P. So you take all the powers of z that is inside f, and what remains is a unit. This is very similar, for example, in number theory. When you have a rational number and you want to find the order of a prime inside that rational number, you take all the powers of P inside that rational number, and what remains is a P unit. And this number M is called the order of P. And what you need to check, which I'll leave it to you to do, is that if you choose a different coordinates, like instead of Z, you pick W, then you get the same number M. the order of vanishing doesn't change. This u of z changes, but the order of vanishing or pole doesn't. So this way, you get a function ord p from the space of non-zero meromorphic functions into Z, and it has the following property that can be easily seen. Property one is that the order of fg at P, order of f at P, plus order of g at P. In other words, this function is a homomorphism from the multiplicative of meromorphic functions to the additive group of Z. The second property is that order of P of f plus g is bigger than minimum of order of P of f and order of P of g. And the property is that order of the constant is 0 for f. So such a function is called a discrete valuation. And what Dedekind and Weber showed in their work is that, in fact, if you only give me K and not the Riemann surface, one can recover the points on X as these valuations. So any point gives you a valuation, and conversely, any valuation comes to a point. Of course, you have to define a certain notion of equivalence of valuations, and equivalence classes of valuations define points. I'm not going to spend too much time today about this idea, although it's a very, very important idea in mathematics. But in future, I don't know if I can get another time to speak more about Roch from the algebraic views or geometric point of view, because today I'm going only to talk about the analytic view of a Riemann-Roch theorem, which is in fact, I think is the simplest one. And the fact about this point of view is that it only works over C. If I want to treat the Riemann-Roch theorem in algebraic manner, I can make it work over any field. So, but anyway, that has some cost. So I have to go and discuss many things like evaluation rings and extend the discrete valuation ring from one field to an extend that field. So it's actually a long story. Okay. So most important property of this ord function is this one. If you give me f x from x to cp1, which is 0, then you can find the ord of p for different points p in x. And almost all of these numbers are 0, because the number of poles and zeros of a function is finite, because x is assumed to be compact. And therefore, I can add these numbers. Yes, that's a finite sum. And the property is that this sum is equal to 0. In other words, any meromorphic function, when you count the number of zeros and poles with multiplicity, has as many zeros as. Hold on for a minute. Let me. Okay. So this sum is equal to 0. And there are different reasons for this fact. I tell you analytic reason why this should be true, and I also can tell you an algebraic reason why it should be true. The analytic reason comes from the Cauchy integration formula. You all have seen such a formula in course that in complex analysis, but this is also true for Riemann surfaces. It says that if you take the integral differential form along some closed path and multiply it by 1 over 2 pi I, the answer is equal to the sum of the residues of poles of omega inside this path. This is integral formula. And as a consequence, you get that the sum of the residues of omega for all points in X is always equal to 0. And why is that? Because you can take your closed path so small that it doesn't contain any poles. And therefore, if you look at outside of this path, then the integral is going to be the sum of all these residues. And if you look at inside this path, the integral is going to sum of 0 residues. So the sum of residues must be 0. So this way you can prove the theorem. Now, why is this related to the ORD function? The reason is very simple. The reason is that if you take df over f as a differential form, then the residue of this form at a given p is the same as the order of vanishing or pole of f at p. And this can be seen very simply by replacing f by z to the power m times u, and then taking the differential. So you see that the m comes out of the, after taking the derivative of z to the power m, it becomes z to the power m minus 1 times n, and then you divide by z to the power m, so m divided by z. So the residue is going to be equal to m. And since the sum of the residues is 0, then therefore the sum of the ORD functions is 0. Now, how do we see this in an algebraic way? Well, the sum of ORD P of F, when P is a pole, or with the negative sign, or the sum of the ORD P of F is a 0, is in fact nothing but the order of inverse of infinity of the order of f inverse of 0, but counting these points with multiple. So you think of f inverse of infinity not as just as a set, but as a multiset. Some of the points inside the preimage should be counted more than once. And so you know that metric function x to cp1 is a branched covering of D. So it's almost always D to 1, except at some ramified points. And at those points, you have to count multiplicities. So count multiplicities, these two numbers are the same and equal to the degree of the covering space. So since these two numbers are the same, and therefore they're, if you add them without the minus sign, we'll get 0. This has advantage of being able to be generalized to the case when you're working over other fields, but to set up the language properly so that you can talk about the degree, because the theory of covering the spaces is a topological theory that only works over C, but you can make this work over any field. Okay. And we come to the point we can define divisors. So any function f will give me a divisor, which I denoted by bracket of f, which is a sum, a formal sum of points Riemann surface with multiplicities given by the ORD function. So this is a finite sum because, as I told you, any function has only finitely many poles and zeros. And this is a divisor of degree 0. So that means that if you add these cities, you get 0. So in general, the divisor on X is such a formal sum where ORD P are integers, and for almost all P's, that means that for all P except finitely many is 0. So an example of such divisor is the divisor of a function, which is sometimes called a principal divisor. So what you can do with divisors is that you can add them, and you can say d1 is bigger than 2 if each coefficient in d1 is bigger than that corresponding coefficient in d2. So you can do things like that. And you can also talk about degree of a divisor, which is the sum of OR P of. So as I told you, degree of any principal is 0, but the converse is not necessarily true. It's not any divisor of degree 0 actually is the divisor of some function. And the obstruction to this problem lies in the genus. The higher the genus, then the larger this obstruction is towards constructing a function out of a degree 0 divisor. Okay. So how do we use this divisor D in order to pin down sub-meromorphic functions inside the space of all meromorphic functions is via this definition. This is one of the more important definitions in the theory of Riemann-Roch, the classical theory of Riemann-Roch. So given a divisor D, I define a subspace of meromorphic function. All meromorphic functions that OR P of F plus OR P of D is bigger than or equal to 0. Okay. So it means that the order of zeros and poles of F are somehow described or determined by the coefficient, the multiplicities inside the device. For example, if the device is 5p1 minus 2p2 minus 3p3, then or the 1 of f must be bigger than or equal to minus 5, or p2 of f must be bigger than or equal to 2, and or p3 of f must be bigger than or equal to 3, and or p of f must be bigger than or equal to 0, all the rest. So it has to be holomorphic at all points except P1. And at P1, it can have a pole, or the pole is at most -5. At P2 and P3, it must vanish of order at least 2 or 3. So this is the space of functions. And this is a subvector space. The only issue that you might raise is that the OR function is not the 0 function. One can formally add 0 to this space, or you can say that this is the space generated by these things. So the 0 function belongs to this. So L of D is a subspace inside all meromorphic functions. And what Riemann was interested was, what is the dimension of this? So he wanted to find a formula that describes this dimension in terms of D. And he was not able to completely find this formula. Such a formula actually does not exist. You can compare L of D with another divisor, and there is a relation. So I'm going to talk what Riemann-Roch really is. But Riemann-Roch is trying to answer this question. What is this dimension? And the first question you might ask yourself is, why is this dimension finite? In fact, it is finite, and Riemann knew about it, and he had a proof also for this. But I'm going to first, before giving you a low-level proof, a common way of showing that this is a high-level way of showing that this is finite using common theories. So remember, I defined this space of functions, L of D. And this is, in fact, global sections of a sheet. And we are talking about global sections of a line bundle inside on a Riemann surface. And let me define for you what this sheet is. So you define OXC on some open set to be the all meromorphic functions U such that OR P of plus OR P of D is bigger than or equal to 0 for P inside U. So now it is clear that if you take U to be the entire space, then you get the pre-definition. But this is a local version of defining that. And this one can show, it's not too hard, it's actually very easy, that OX of T is locally free of OX modules of rank 1. And all these are named for line bundles. And in fact, it is true that any line bundle on X is in this form. But if you have two Ds such that their difference is a principal divisor, then these two Ds will give you the same line bundle. So one of the important things that I had to define, but I forgot, is this notion of equivalence of divisors. We say D1 are equivalent if and only if D1 minus D2 is divisor of some function. So since degree of a principal divisor is 0, one of the necessary conditions for two divisors to be equivalent is that they have the same degrees. But of course, this is not enough. But equivalent divisors have the same degrees. Another thing about equivalent divisors, this space L of D actually is isomorphic to L of D2. L of D1 and L of D2 are isomorphic as vector spaces if and D2 are equivalent. And the reason for this is very simple, because we want the divisor of G plus D1 to be positive, and therefore divisor of G plus D2 plus divisor of F is positive. And this means that divisor of Fg plus D2 is positive, if and only if. So in other words, if you have a G inside D2, then F times G, D1, F times G belongs to L of D2. So multiplication by F is such an isomorphism. So not only these spaces are isomorphic, but the isomorphism is actually very explicit. It can be constructed by F, just multiply by F. So in the statement of Riemann-Roch, you can always replace a divisor by another divisor that is equivalent to it, and nothing will change in the statement because degree and L of D doesn't change, and these are the only things that are that appear in the formula. Now I was about to tell you why the dimension of this space is finite, and I told you that L of D is the zeroth cohomology of X with this. And this is a fancy way of saying that we take the global sections of this sheet. Serre, in a very famous paper about algebraic coherent sheets, has proved that all these cohomologies are finite dimensional. So in fact, there is a result of this that says that if X is a projective variety and F is a coherent residual. If you don't know these terms, that's okay. We're going to talk about this actually during this course. These are important concepts, and we will actually use them. But if you don't know, it's okay because we'll probably spend some time explaining that. That proves that all homology groups are finite dimensional complex vector spaces. Yeah, these are finite dimensional. So the global sections of a line bundle or global sections of any vector bundle is going to be a finite dimensional space as long as the manifold that you over is in the language of analytic varieties, manifold, that means that they're compact. So for compact complex manifolds, the of global sections of any vector bundle is finite dimensional. Okay, but of course this is like using a sledgehammer to break a small knot, and of the fact that L of t dimensional is in fact very simple. Let me try to explain why is it true in low using low technology. First observation is that if degree of a divisor is less than 0, then L of t is trivial. Why is this true? Well, if you have an f inside t, a non-zero f, then the divisor of f plus must be positive. And that means that degree of this divisor must be positive. But we know the degree of a principal divisor is 0. So the degree of t must be positive. So that means that if degree of t is negative, there is no such non-zero f inside L of t, and L of t must be trivial. The second observation, which is also as simple and simpler, is that if d1 is smaller than or equal to d2, then L of d1 is a subset of L of t. The reason is that function, the divisor of a function added with d1 is positive, then added with d2 is also positive because d2 is bigger. All the coefficients of d2 are bigger than d1. And this implies that you have such an inclusion. So all I need to prove in order to show that L of d is finite is to prove something like this. L of d plus p is less than or equal to L of d plus 1. So by adding a point to the divisor, you just increase the dimension at most by 1. You can leave it unchanged, stay the same. L of d plus p is equal to, because of course bigger than L of d. If d1 is less than d2, then this space is the space of that one. So this shows that if you add a point to a divisor, the space will be increased at most by 1. And therefore, this implies not only the dimension is finite, but L of d is less than degree of d plus 1. Give me a minute, I'll be back. Sorry. So, way to prove this is a simple induction on degree. For example, we know that it's when degree of d is -1. And then from there on, you can show that it is true for any divisor. And to be completely correct, I have to assume that degree of D must be bigger than or equal to -1, because talking about negative dimensions is a little bit silly. So we know what L of D is negative. So this is only for the case when degrees. Okay. And how do I prove such an inequality? The proof is one. So you take an F inside L of D plus P minus L of D. If such an F doesn't exist, that means that L of D plus P is the same as D, so the dimensions are the same. If such an F exists, then that means that the order of P of F is exactly the order of P of D plus 1, because minus or plus, minus. And therefore, you can see that L of D plus P is L of D sum with a copy of this F. Because any function that you have inside L of D plus P, by a correct multiple of, you can kill off that high order pole at P and make it inside L of D. So if there exists such a function F, then you can simply prove that L of D plus P is L of D plus C times F. That means that dimension is increased exactly by 1. Okay. All right. So this is an inequality. Of course, this is not Riemann's inequality. Riemann proved something like this. That this degree of D plus 1 is L of D, which we just showed that it's positive, is bonded from above. And the bond that you have for this is nothing but thickness of the Riemann surface that you work with. So this is Riemann's contribution to Riemann-Roch. So it says that L of D is bigger than or equal to degree of D plus 1 minus, yeah. And how much bigger it is, that's the part that comes into play. Roch proved that L of D is equal to degree of D plus 1 minus G plus L of K minus D. And K is a divisor that's called the canonical divisor. The reason that I put there inside the quotation mark is that we will see shortly that this divisor is not well defined. We cannot really define the canonical divisor, but we can define a class. So all these different definitions are going to be equivalent to each other, these equivalents of divisor I talked about. So the difference of any two of such canonical divisors is going to be divisor of a function. And therefore, as long as we care about the dimension of the space, it doesn't matter. Any of these Ks will do the same. It will be fine for us because they all give the same number here as L of K minus D. So what can we say about this mysterious K? First of all, if you let D grow, let's see what happens. L of 0 is equal to 0 minus G plus L of K. Now, what is L of 0? I had to tell you about this, I forgot. L of 0 is the space of functions that are holomorphic on X, because this means that f such that ord p of f is bigger than or equal to 0. And do we have a function that is holomorphic x? Well, yes, constant functions are holomorphic on x, but do we have any other holomorphic function on x? And the answer is no, because we have assumed x is fact. So any holomorphic function is going to be bounded, and by Liouville's theorem, such functions are constant. So L of 0 is just C. This means that the dimension is 1 here, and the two ones cancel, and we get L of k. So one can define, once I tell you what the definition of K is, one can define genus by the dimension of the space L of K. That's one definition of the genus. What else can be derived from Riemann-Roch formula? The formula that I just wrote down the statement of it without proof, and I will try to prove with the theorem for the rest of this. The other you can derive is that if you put d equal to, you get L of k is equal to the degree of k plus 1 minus g plus L of 0. L of k, we just found this g. Degree of k, we don't know. Let it be there. 1 minus g plus this is 1. And this way you can find degree of k to be 2g minus 2. For some of you, a little bit of apology, might see that 2g minus 2 is the negative of the Euler character of the Riemann surface. 2 minus 2g is the Euler characteristic. And it is actually not a coincidence. The relation between the degree of k and the Euler characteristic is something that I can explain, but let me just leave it out for now. And if I have time, I'll explain it. So we know a lot about it, but we don't know what it is. Definition is very simple, in fact. Take any meromorphic one form on x, say omega, and define k to be the divisor of this form. And this is very similar to the way that we find divisor of a function. It's ord p omega. So you see whether this form vanishes or has a pole. And for those points that has a 0 or a pole, you take the order of that form, and this way you define k. Now, why is this well defined? Because it is easy to see any meromorphic one forms, omega and omega prime, related like this. Omega prime is f times omega for some meromorphic function. And the reason for this is just looking what is the definition of a meromorphic. A meromorphic form is given by a collection of, let's use another letter, let's say HU of Z DZs, and each of these open charts U. And this relation should be like this. HU of Z, HU prime of Z prime is HU of Z times derivative of Z with respect to Z prime. So if you go from one chart to another, these local representations of your morphic one form behave like this by this formula of coordinates. And this implies that if you have two such morphic forms, if you take the quotient, these factors of derivative of z with respect to z prime will cancel. And so these functions are equal on the points where u and u prime are both defined. And this says that this is the totality of these quotients, in fact, a well-defined meromorphic function f, and this tells you that why the one forms are related like this. And this implies that the class or the divisor of this meromorphic form is independent of the choice of omega. Okay. So now I have defined everything in the Riemann-Roch formula, and what remains is how to prove it. Okay. But before going into proof, I want to tell you a few applications of Riemann-Roch. Actually, maybe just one application. Let me tell you a little bit about this meromorphic one form. And the first question that you might ask is that why such a meromorphic one form exists to begin with. We want a non-meromorphic one form to take its divisor, and why every Riemann surface has such a meromorphic one form. And the answer to this question has the same difficulty as the answer to the question that why we have a meromorphic function on Riemann surface. Because once you have such a function, then you can take df, and df is a meromorphic one form. And what is df? Well, you have such a meromorphic one form on CP1 dz. So think of coordinate z on the complexes, and dz is a meromorphic one form. Well, it's never zero on C, and it doesn't have any pole on C, but at infinity, it does actually have a pole. Why? How do we see such a pole? Well, you have to use the change of variables. So infinity corresponds to zero under this change of variables, and then when you take dw, you get minus 1 over z squared dz. And then you see that this one form of the pole of order 2 at infinity. And in other words, the canonical divisor on CP1 is 2 times infinity. And the degree of this k is -2, as it should be, because it's 2 times 0 minus 2. And the space of, that's the canonical divisor on 1. And well, if you have a one form on CP1, you can pull it back using f. So you take f star z, and this is the same thing as df. This is the hard way of defining what df is the pullback of dz. Okay. So this way you can always find a meromorphic one form on any Riemann surface as long as you have a non-constant function. Let me give you another example of such canonical form. For example, on genus 1. When genus is 1, one surface is C divided by lattice. And then you can also define this dz here. And dz is well defined because even if z is not well defined, but dz is, because the differences of z's are by elements on the lattice, therefore the differential of it is. So dz is a well-defined one form on this torus, is never zero and doesn't have any poles. And therefore the canonical divisor associated to this form is just simply 0. Of this k is also 0, which is 2 times 1 minus 2, 2g minus 2. So everything works out so far. So that means that there is no contradiction. Okay. So what is the statement of Riemann-Roch for genus 1 curves? It's L of D is the degree of D plus 1 minus 1. The L of 0 minus D. And if degree of D is bigger than 0, this is 0. So that means that L of is degree of D plus, just degree of D. So this is the simplest, I think, version of Riemann-Roch for the curves of genus 1, that the L of D is degree of D. It's nothing but that. So this is a formula that actually works perfectly without any other terms in it. And for degree of D less than 0, we know that L of D. Okay. So why is this important? And why do we care about this L of D? Now, this application probably tells you some of the values or importances in Riemann-Roch formula. I'm going to prove using Riemann-Roch that any genus 1 curve is given by equation, something like y equals x cubed plus ax plus b. So this is the counter to what I said. So I said that these equations give you genus 1 curves. I'm telling you that actually any genus 1 curve is in this form. And this can be proved using Riemann-Roch as follows. You pick a point P inside X, and you look at L of NP for different values of N. For example, N equals 0, 1, 2, 3, 4, 5, and 6. Okay, so L of 0 is just 1 because constants. L of P is degree of 1, that's just 1 again. This is 2, this is 3, this is 4, this is 6. So this is just constants. And that's constants also. So there is no meromorphic meromorphic function on an elliptic curve with only one simple pole. It must have one simple pole. If you think about the Weierstrass P function, you see that double poles. Okay, so we call this constant function 1. Then you go into the pole order 2, you add 1 to the dimension. So there is a function x with pole of order 2. When you go to the poles of order 3, the dimension is added again by 1. So you have y with pole of order. Now, if you want pole of order 4, you can construct it out of x. X squared is such a function. And since the dimension is only added by 1, so that means the only function that you have of pole of order 4. For pole of order 5, you can multiply x and y. Pole is, remember, x has pole of order 2, y has pole of order 3, so the product has pole of order 5. And then once you want to construct pole of order 6, there are 2 ways to do it. You can raise x to the power 3, or you can raise y to the power 2. Both of these functions have poles of order 6. Now what has happened? We have constructed 1, 2, 3, 4, 5, 6, and 7 functions in a space that has dimension 6. So what does it mean? You have 7 functions in a space of dimension 6. That means that there must be some linear relation. So that means that you have y squared plus by xy plus c times is equal to d times x cubed plus e times s squared plus f times x plus 2. So you must have an equation like this. And then a simple change of variables by replacing x with, say, x plus some constant, or y by y plus some multiple of x plus a constant. You can make it to the more appealing form of y squared equals x cubed plus ax squared. So Riemann-Roch actually showed that any genus 1 curve over C is given by such an equation, at least the affine part of it. We have to make it homogeneous to make it the complete curve. Okay. How much more time do I have?
I don't know until I guess until 2. What time is it now? About
half maybe.
Yeah, half an hour.
Okay. All right. So I want to give a proof of Riemann-Roch theorem. When you're working a plane curve given by a simple polynomial equation P of degree n, for example, inside CP. This is not the most general proof that one can find for Riemann-Roch. It has this hypothesis that the equation of this Riemann surface is a single equation inside two, but at least it has the advantage of being simple and can be understood. It doesn't use very high-tech and advanced techniques of, say, like sheet cohomology or things like that. But that doesn't mean that I'm not going to give a more general or more algebraic proof of Riemann-Roch. I'm going to ask Mehdi to give me another time for me to explain these advanced proofs that are actually more general. They work over any field, not just C. Okay. To do this, I want to warm up by talking a little bit about Riemann-Hurwitz formula. And telling you a little bit about, sorry. Telling you a little bit more about this canonical divisor K. Remember, we found out that K is G and degree of K is 2G minus 2. And we derived these formulas using Riemann-Roch formula. And now I want to tell you, actually, you don't really need Riemann-Roch to know about these formulas. These can be derived even without Riemann-Roch. To do this, let me first try to understand what is L of K. So L of K is the functions f such that divisor f plus divisor of omega is bigger than or equal to 0. So this means that functions f such that divisor of f is bigger than or equal to 0. And this is the space of all holomorphic one forms. I denote this by omega x. So the formula L of K equals G tells you that the dimension of holomorphic one forms on X is equal to genus. This is called the geometric genus. And it's denoted by P of G. And this can be defined for any complex manifold, which you can this to be the dimension of the omega n of x, where is the dimension of x. In the case when x is one-dimensional, as a Riemann surface, then this is one form. But if you're working over complex surfaces, you can define geometric genus to be the dimension of two forms. If you work over a threefold, you can take three forms and so on. And it is finite dimensional, as I said, that the global sections of any bundle over a complex manifold, compact complex manifold, is finite dimensional. And the name geometric is because there is another version of genus that is called arithmetic genus. Of arithmetic. In the case of a Riemann surfaces, it's the dimension of h1 of x and O of x. And in the case of higher dimensions, it's going to be more complicated. It's going to be something like Euler characteristic. You have to take alternating sums of these dimensions. But this is the simplest. And there is a way to interpret h1 of x and O of x using classical language as the space of obstructions to a problem that is called Mittag-Leffler. It's funny because until quite recently, I have always thought that Leffler is the name of two mathematicians, but in fact, it's just one mathematician. Mittag-Leffler is the name of one person. And the problem that he studied in 19th century is about the problem of finding meromorphic functions on E with prescribed singular parts. So you have some point like A, you give me the singular part of your function. So that means that the c minus a to the power -1, c minus 2, c minus a to the power -2 up to c minus n, z minus a to the power -n. And you have it for a finite or infinite number of points. Mittag-Leffler showed that actually, as long as these points do not accumulate discrete, then you can always find a meromorphic function on C whose singular parts are given by the equations. So that means that if you write the Laurent power series for F around A, the part with negative powers is exactly the one given here. Now, if you study this problem on a Riemann surface, not just on C, you see that this problem doesn't have an answer, even in the case when you have a finite number of points. And the obstruction to find this answer is described by a space that in modern language is nothing but this sheaf cohomology of x, the first sheaf cohomology of x with coefficients in O of x. But in fact, one can describe it even more concrete by the space dells. This was described by Andre Weil, and proof of Riemann-Roch given by Andre Weil that I'm going to explain, but not today. And that proof has the advantage of being able to be generalized and work for any field. Okay. So one of the difficulties in proving Riemann-Roch is all these different ways of defining genus. Define genus topologically as the number of handles, numbers that you have in the Riemann surface. You can define it geometrically using the dimension of the space of holomorphic one forms. Define it arithmetically using this obstruction to Mittag-Leffler problem. And all these three numbers are equal. And this is actually one of the contributions of Roch. He proved that they're all. But why do I say that one can prove these properties of the canonical divisor without the use of Riemann-Roch? Why can we show that L of k, for example, is G? Well, omega 1 of x, the space of all holomorphic one forms, these are in fact, in fact embeds inside the first cohomology of x with coefficients in C, using theorem theory. How do we get an element in H1, the cohomology of x? We have to find a differential one form that is closed. And all these differential forms that are holomorphic are closed. Why? Because if you write one of these locally as fz dz, and you take the differential of it, it's going to be df over dz, dz plus df over dz bar, dz. Now, dz is 0, and df over dz bar is 0 because f is assumed to be holomorphic. And df over dz bar equals 0 is the compact way of writing Cauchy-Riemann equations that you all learned from your elementary course in complex function theory. So this implies that d of omega is 0. So any holomorphic one form gives you a cohomology class, the first cohomology class. And why is this embedding? This is that we can't find a holomorphic function whose differential is omega, because there are no holomorphic functions on x because of Liouville's theorem. They're only constant functions, and the only omega that is equal to d of some constant function is 0. So this means that you have such an embedding. And similarly, you can embed anti-holomorphic one form, the complex conjugate. And using a little bit of complex geometry, namely the Dolbeault theorem, I'm not going to discuss this today, but probably we have to also talk about this in some lectures in future. H1 of x is the direct sum of these two copies. And now this is, we all know the 2D dimensional space. And the of them must be G dimensional. So that implies that dimension of omega 1 is G. Why? Because they're isomorphic. Of course, the complex conjugation is an isomorphism between these two spaces. Okay, so that's one part of what we already knew from Riemann-Roch theorem. This part. And now, why degree of k is equal to g minus 2? Okay. So you have meromorphic function like this. You can think of it as a branched d to 1 covering. And you can take infinity at CP1 ramified. That means that the F inverse of infinity is really a set with D elements. Okay, so now what can we say about divisor of df? So as you remember, df is the pullback of dz. So we know d has a pole at infinity of order -2. And therefore, if you look back on x, you get d copies of these infinities on x, and each of them gives you a pole of order negative. So you have -2d coming from these. So I'm trying to calculate degree of k. So you get a -2d coming from these poles. And now, what about z of df? df f prime dz, right? So the zeros of this form are coming from the zeros of derivative of f. That means that they're coming from ramified points. So this sigma of ramification index minus 1. What is the ramification index? The name might be scary, but the definition is very simple. Locally, if you look at f, when the pullback of a point multiplicity, f like z to some power. And this power e is called ramification index. So locally, f can be written as z to some power, and this e is ramification. Of course, if you take derivative of f, you get z to the power e minus 1. So therefore, the order of vanishing of this function is going to be the ramification index minus 1. So now I need to find this sigma of ei minus 1. And this is where Hurwitz formula comes into play. If you have already seen this formula in your topology courses, but it is actually intuitively simple. Suppose you have, let me do it in a more general way. So you have a branch, not a branch, so suppose it is a real honest covering. Covering map, degree D. So the Riemann-Hurwitz tries to understand the relation between the Euler characteristic of X and the Euler characteristic of Y. And tries this question if there is any relation between these two numbers. And the answer is yes. The Euler characteristic of X is D times Euler characteristic of Y, where D is the order of this covering map. Why? Because if you do a relation on Y, so it has some numbers of and some number of edges and some number of two cells. If you pull it back using F, each of these will be multiplied by D. If you have like K points, it will become K times D points on X. If you have like K prime edges, it becomes K prime times D edges on X, and so on. And since the Euler characteristic is the number of 0 cells minus number of 1 cells plus number of cells, then everything will be multiplied by D. Okay. Now, what if the covering map is branched? So in this case, instead of having D times the number of points, this many points removed, because the points, the ramified points, they have multiplicities, and the Euler characteristic doesn't see these multiplicities. So this is actually a true formula that is the content of Riemann-Hurwitz. And I prove very intuitively, also prove it more rigorously by removing these bad points and talk about the Euler characteristic of X punctured with some points. So instead of taking the Euler characteristic of X, you take the Euler of X minus few points. And it's not too hard to show that the Euler characteristic of X minus, say, K points is the Euler characteristic of X minus K. This is true. So using this, I can actually prove this regularly. So now let's see what happens if Y is CP1. In this case, we get the Euler characteristic of X is 2 minus 2G minus sigma. Oh, sorry. Minus should be written here. because the number of points is counted on the other side. So 2 minus 2g. Euler characteristic of the sphere is 2. It's 2d minus sigma I minus 1. Okay. If you come back here with degree of k was negative 2b plus I minus 1. And you see that the degree of k of this number is that's 2g minus 2. So what I was trying to say, I don't know if I was successful in conveying the idea, is that Riemann-Hurwitz formula alone will suffice to prove that the degree of the canonical divisor is 2g minus 2. And you don't really need the Riemann-Roch theorem. In fact, for algebraic curve given by an equation like this, P of x, y, and z equals 0, one can try to write down an explicit holomorphic or meromorphic one form on x and find what the degree of this explicit meromorphic one form is. 2g minus 2 that way. Let me give you an exercise which I think you should try to do using Riemann-Hurwitz formula. And that's this. If you give an equation of degree b that is smooth, then the genus of the curve that is defined using this equation is d minus 1 minus 2 divided by 3. So, for example, if the degree of this equation is 3, then 3 minus 1 times 3 minus 2 is 2, divided by 2 is 1. So a cubic equation will give you a genus 1. If you have a degree 4 equation, you have 3 times 2, 6 divided by 2, so you get a genus 3 equation using degree 4, right? Yeah. So any genus can be written as d minus 1 times d minus 2 divided by 2. So this in fact shows some constraints about some Riemann surfaces that cannot be expressed as an equation of single polynomial of degree b. But I expect that this can be any number. Okay, let's think about it in some other time. Okay. So I have like 10 minutes. And this 10 minutes, I want to give you some heuristics that why Riemann-Roch theorem is true. So I take this P of x, y, z equals 0 inside CP2, and I take, say, L equals ax plus by plus cz equals 0, and intersect this line with this curve, and this I construct a divisor. So by IP of L of x, L comma x, I mean the number of the multiple of P on X that lies on L. So when you take L intersection K, you get certain points. So suppose the degree of P is N. And this construct a divisor is effective, meaning that these numbers are non-negative. I define this to be H. So what I want to do now is I will see, can I find L of MH, or can I approximate it, how big it is? And can I compare that with the prediction that Riemann-Roch tells me that it should be? So that's what I want to do this last few minutes. Okay. First thing, can I find degree of H? What is degree of H? This means that the number of points that intersect this line counted with multiplicity. Now, probably this reminds you of the Zoo theorem. If you have two equations, one of degree n, another one of degree 1, they will have n in common, counted with multiplicities inside the projected plane. So this degree is nothing but n, like the Zoo. Another thing that I want to tell you is that it doesn't really matter which line you pick. Any line that you pick is going to give you the same divisor class. So if I give you another line, a prime x plus b y c prime is equal to 0, the divisor that is defined using this line and the divisor defined using this first line are going to be equivalent to each other. And why? Because you have a function, which is the quotient of these two. And the difference between the zeros of the first, the intersection of the first function with x and the intersection of the second function with f, with x, is this function f. So it doesn't really matter which line to pick. And at the beginning, you can pick a line that actually intersects properly this curve, and you don't really have to worry about these multiplicities. The multiplicities are all 1. Okay. Now, what can I say L of MH? So if you give me a polynomial of degree equal to m, then the divisor of this q of x, y, z and the divisor of ax plus by plus cz to the power m are going to be equivalent to each other. And therefore, this is going to be a function inside L of m. So this way, I constructed a lot of elements inside L of mh. And I want to count the dimension of this space. So the space of all functions of this form. So the answer is simple. All you need to do is to find the dimension of the space of homogeneous polynomials in 3 variables of degree m. And this is m plus 2 choose 2. M plus 2 choose 2. This is m plus 2 times m plus divided by 3. But this is not completely correct because some of these functions will be equal. So when two such functions are equal on x, this happens exactly when the difference is a multiple of p. Remember that the equation of your curve is given by this equation. And therefore, if two functions, there's two q's, like q2, their difference is a multiple of p, then they are the same. So this means that we have to subtract q's which are of this form, p times q prime, where the degree of q is m minus p, m minus n. The degree of p is assumed to be n. So we take m to be bigger than or equal to n, and therefore the number of these functions minus n is 2, which is m minus n plus b times m minus n plus 1 divided by. So all you need to do is you have to subtract these two numbers. So L of NH is bigger than or equal to this difference. And this can be done in your leisure, but trust me, the answer is going to be mn minus n minus 1 times n minus 2 divided by 2 plus 1. And this can be written as degree of mh minus the genus plus 1. And you see that this is exactly the Riemann inequality for H. And it is not hard to derive the exact Riemann-Roch out of these calculations here. But since I'm running out of time, I'm going to stop here and try to explain this maybe on Saturday when we have more time and we are actually not this tired. So at the end, I'm going to give you a few references. One of them is videos on YouTube by Borchert. If you search the name Borchert and Riemann-Roch, find some videos that I've used when I was preparing for this talk, and those are really, really good. The other reference is if you go to Jill Kitchen website, under teaching, he has some notes on algebraic curves. Which is very nice. And the third reference that I'm going to tell you is a book by Artin called Algebraic Numbers and Algebraic Functions. And chapter 14 of that is about Riemann-Roch. It has a complete proof of, actually it has two different proofs for Riemann-Roch, and the Riemann-Roch that is proved in that book is actually for any field K, not even necessarily algebraically closed. So it's very general. And the final reference I should give you is the Kempf. Called Algebraic Varieties. In that book, it has a proof in Riemann-Roch using the language of sheaves and cohomology of sheaves. So this is analytic proof that I was trying to just explain today, but I ran out of time. This is algebraic proof using the language of Adels and Weil theory of Adels and Adels. And this is geometric proof using algebraic geometry, using sheaf cohomology. So if I have time, and I hope that Mehdi give me this like 1 or 2 lectures, I'm going to explain to you all these 3 different versions of Riemann-Roch, because as I said, if you look at the same theorem from different angles, you have a better understanding of it. And I believe that if one sees only one of these proofs, he hasn't really understood what Riemann-Roch is about. But if you see all three together, then you have a much understanding of the meaning of this theorem. Okay, so I stop. Thank you.